Okay, this is the okay, so 334. Let's get started. Today we talk about lecture number 11, which is volume stability. Okay, so mainly about shrinkage of concrete and also creep. Okay. We discussed shrinkage and creep a little bit before this class. Okay. But here is the basic summary about shrinkage and creep, which is a very important property for concrete. Okay. Because concrete is very brittle. Shrinkage of concrete may cause concrete to crack. Okay. So that will reduce the durability and also the strength of concrete. First of all, what causes volumetric change of concrete? And that's many different reasons, as you can see from here. Okay. Temperature change. Okay. Higher temperature, the concrete will expand. Lower temperature, concrete will shrink. Okay, so that's true for almost all type of materials. Yeah. Mechanical loading. Okay, if the concrete under load, then it will creep depending on it is under compression or tension. Okay, under compression, the volume dimension will become smaller. Okay, and also relaxation. Okay, if we keep the same deformation, then the internal stress will become smaller. Okay. Moisture change, for example, drain shrinkage. Okay. That's the shrinkage dealing with moisture loss of concrete. Hydration, which is the chemical reaction between cement and water, that will cause volume change of concrete. In that case, we call that chemical shrinkage. And harmful chemical reactions, carbonation, sulfate attack, and ASR, all will cause concrete to either shrink or expand. Okay. Okay. For shrinkage, which is volumetric change due to loss of water, we have around 5 different types, okay, including plastic shrinkage, which is the shrinkage due to loss of water to the air in fresh concrete. Okay. Dry shrinkage is loss of water to atmosphere when concrete hardens after concrete sets. Chemical shrinkage is reduction in the total volume of solid plus liquid during the hydration process. Okay. And autogeneous shrinkage, which is caused by so-called self-desiccation. That is loss of water or drying internally due to hydration. Okay. Autogeneous shrinkage only occurs for concrete with very low water to cement ratio. And then carbonation, this is the reaction between CO2, which is from the air, with calcium hydroxide from hydration of Portland cement. Okay. So that's a 5 different type of volumetric change because loss of water. So let's look at plastic shrinkage first. So plastic shrinkage occurs when the concrete is in the plastic state before initial set time. Okay. For the first 3-4 hours normally. Okay. At that time, concrete at the surface is already stiff, but not strong enough. Okay. Plastic shrinkage will accelerate with higher water evaporation rate due to high temperature, lower relative humidity, or higher wind speed. Okay. Or it caused by suction of water by surrounding structures. For example, you do some repair of concrete, concrete or the surrounding structure around the new concrete may suck the water out of the new concrete. That may also cause plastic shrinkage. So plastic shrinkage can cause cracks, which is not very deep, around 1-2 inch on the surface. The spacing between the cracks around 1 feet to about 3 feet. Okay. So how we can reduce the plastic shrinkage? Okay, we could moisten the surrounding structures. Okay. We could also increase the amount of aggregate if we could, okay. Because aggregate will not shrink. Okay. Only cement paste will shrink. We can also use windbreak, sand sheet, fogging, use plastic sheets to cover the concrete, cooling, wetting of aggregate, so that can reduce the temperature, providing extra water. We could even use fibers. Okay, we'll talk about fiber reinforced concrete in future lectures. By putting small amount of fibers, we can reduce the size of the crack, such as the length of the crack. Okay. Here shows how different dosage of fibers can reduce the length of crack, or the percentage of control crack area. So increase the dosage of the fiber, we can reduce the length of the crack and also the total area of crack. Dry shrinkage is caused by loss of water to the air after concrete hardens. So in hardened concrete, okay. So dry shrinkage occurs when pore water diffuses to the surface, and then water evaporates to the air. Okay. So the risk will increase as the porosity or the diffusivity of the concrete goes up. Okay, because higher porosity, higher diffusivity, the water will be easier to evaporate. Okay. And dry shrinkage is the reason we put upper limit on the water to cement ratio, because the higher the water cement ratio, the water will easy to evaporate to the air, and also the concrete has more water. Okay, so remember, dry shrinkage is the reason we put upper limit on the water cement ratio. And here shows shrinkage of concrete over time. Okay, so during drying process, shrinkage will go higher. If we rewet the concrete, for example, we submerge the concrete in underwater, then part of the shrinkage will be reversible. But part of concrete, the shrinkage will not be irreversible. Okay, so why that's the case? We'll talk about that in a moment. So this is old slides. We talk about the water in hydrated cement paste from lecture number 4. Okay, and we know we have different type of water, such as interlayer water or the gel water between the CEE688 sheets. Okay, and also we have capillary water, adsorptive water, and chemically combined water. Okay, the shrinkage of concrete is caused by slippage between the CEE688 sheets. If the slippage occurs, and then the shrinkage is not reversible. Okay, that's the reason why when all shrinkage occurs, even if we put the concrete back to water, part of the shrinkage is irreversible. Okay, that is because shrinkage is caused by loss of water in different part of the concrete. Okay. This curve is very useful, showing us how the shrinkage developed over the weight loss. due to the water loss in concrete. Okay. And we can see, depending on the relative humidity inside the concrete, okay, the water will lose from different parts of concrete. For example, region 1, which is between 100% to 90% of RH, that is water loss from the larger capillary pores, the pores with larger size. And region 2, which is between 90 to 55% RH, okay, that is the shrinkage is caused by loss of water from the smaller capillary pores. Okay. And when water loss from the smaller pores, that will increase the shrinkage stress. As a result, for the same amount of loss of water, the shrinkage will be higher when the water is lost from the smaller pores. Okay. Again, we'll talk more about this. Okay. Region 3 is between 10% to 55% RH. So that is loss of water from absorbed water on solid surface, which is here. Okay, absorbed water, which is a blue circle on the surface of the solid concrete. And region 4 is between 10% RH to 105 degrees Celsius. Okay, so that is loss of water from the gel water, which is here. Okay, the green cross, the interlayer water of the gel water between the CSH sheets. Okay. So loss of that water will cause shrinkage in region 4. And region 5 is due to loss of water by decomposition of CSH. So we lost this chemically combined water in CSH. So that is about 102 degrees, about 5 degrees Celsius. Okay. So we can also see the loss of water in different regions, the slope is different, which means for the same amount of water reduction, shrinkage value will also be different. So dry shrinkage is, the rate of dry shrinkage is size dependent, because dry shrinkage is a surface phenomenon. The water needs to be lost to the atmosphere. So the more surface to volume ratio, the dry shrinkage will be faster. Okay. However, the ultimate value of dry shrinkage will be the same, as we can see from here. So street concrete has the same water cement ratio, same volume fraction. The difference is the surface to volume ratio. Higher surface to volume ratio, the shrinkage rate will be higher, but the final shrinkage value will be the same. Okay. So dry shrinkage rate is size dependent, but the final shrinkage will be the same. So that is dry shrinkage. Then let's look at a third type of shrinkage. So chemical shrinkage. So chemical shrinkage is a reduction in absolute volume of solid plus liquid during the hydration process. For example, CSH plus water, we know we're going to have calcium hydroxide plus CSH. So this is one of the chemical reaction. This will cause reduction of solid and liquid volume. Okay, as we can see from here, after 100% of hydration, we have around 7% reduction in total solid plus liquid volume, which means we're going to have around 7% of voids generated in cement paste. Okay, why we have voids generated in concrete? Because remember, when concrete set within the 4 to 8 hours, okay, so after the initial set, the total volume of concrete will not change too much. But hydration will goes up and the volume will continue to be reduced. So that means we have tiny pores generated in cement paste. Okay, so actually chemical shrinkage is the reason we have small capillary pores in concrete. So this is due to the 7% reduction in the volume. Okay. And then let's look at autogeneous shrinkage and how autogeneous shrinkage is caused by chemical shrinkage. Okay. We know chemical shrinkage is caused by hydration, the chemical reaction. Okay. Chemical shrinkage, autogeneous shrinkage is caused by self-desiccation. It's drying off the concrete not to the air, like in the case of dry shrinkage. It's caused by internal drying because the water cement ratio is very low. Okay. So internal drying is caused by hydration or chemical shrinkage. Okay. So let's see this experiment. Okay. So let's say we wrap the cement paste. At the beginning, it is unhydrated cement paste with water, okay, with aluminum sheets. So that will prevent moisture change between the sample and the air, which means there will be no dry shrinkage and no plastic shrinkage. Okay. Right. And we know because of hydration, we have chemical shrinkage. Okay. The chemical shrinkage before concrete set doesn't really matter because concrete is very soft. If the concrete has some small amount of shrinkage, the concrete will not crack because concrete is soft. Okay. But after concrete set, okay, the total external volume cannot change freely because concrete becomes a solid. Okay. So after initial set, the paste will try to resist this deformation due to chemical shrinkage. So that will cause formation of tiny voids in the microstructure. Okay. So let's look at the third one. This is a paste after the final set. Okay. So before set, we could have some small amount of autogeneous shrinkage. That is before concrete set. It doesn't really matter. Okay. But after set, the concrete can shrink because we have pores generated. If the pores dries out, that will cause concrete to shrink due to the shrinkage stress, which we will quantify that in a moment. Okay. So we have some autogeneous shrinkage after concrete set. And also within the concrete, with the cement paste, we have this air, small air bubbles. We call that pores within the cement paste. So that's the voids generated by hydration. And if we add this volume of the pores together, okay, we call that cumulative voids. Okay. And look at the last picture. We can further classify the chemical shrinkage, which is the total reduction in the volume, okay, as two parts. So one is the volume of voids, which is this part, cumulative voids. And the other part is autogeneous shrinkage, which is apparent volume reduction, or the change of the volume and the length of the specimen. Okay. And that part we can measure. So autogeneous shrinkage is caused by chemical shrinkage because without chemical shrinkage, we will not have the pores, and the pores will not dry out. Okay. And autogeneous shrinkage only occurs in concrete with pretty low water to cement ratio. As we can see from here, one concrete has 0.5 W/C, okay, which does not have much autogeneous shrinkage at all. Okay, but this is only 248 hours. Concrete with low water cement ratio, they could have a lot of autogeneous shrinkage in the first 2 or 3 days. Okay, so about 300 microstrain in the first 2 days for this concrete. Right. So if we observe a shrinkage over long term, over 3 months, for example, here in the right. Okay. So the total shrinkage is this line, okay, the black line. And we can, using different measurements to quantify how much this total shrinkage is coming from temperature change, in the case of thermal shrinkage, how much this shrinkage is coming from drying shrinkage, which is due to drying of the concrete to the air, so the water come to the air, or is caused by autogeneous shrinkage, or drying of the concrete due to self-desiccation. Okay. Remember, the total shrinkage could be a combination of 2 or more type of shrinkage, as in this case. So autogeneous shrinkage occurs in sealed concrete when we wrap up the concrete with plastic sheets or aluminum foil, okay, or when the concrete is very dense. So if the concrete has very low water cement ratio plus it has a certain percentage of silica film, the pore structure will become very, very dense. Okay. If that's the case, even if we cure the concrete, we spray some water on surface of concrete, the concrete can still has autogeneous shrinkage because the pore structure is very dense that the water from curing will not penetrate and increase RH inside the concrete. Okay. And autogeneous shrinkage is dictated by water cement ratio. Only occurs when the water cement ratio below around 0.42. Okay. And it has the same mechanism as drying shrinkage, which is the drying of the pores. Okay. The difference between autogeneous shrinkage and drying shrinkage is, for drying shrinkage, the drying pores is due to evaporation. So the water goes to the air. For autogeneous shrinkage, the drying pores is coming from self-desiccation, the drying of pores due to hydration. And autogeneous shrinkage is the reason we put the lower limit on water to cement ratio, because the lower the water to cement ratio, the higher the autogeneous shrinkage. Okay, so when you design high strength concrete, for example, you should be very careful about how much autogeneous shrinkage the concrete will have. Okay, if the concrete cracks, no matter how strong you design a concrete, then the concrete will be not strong and not durable. And traditional curing, by cover the concrete with plastic sheets or spray water on top of the concrete, will not be very effective because, again, the concrete is very dense, permeability is very low, so external curing is not very effective. So why autogeneous shrinkage only occurs in low water cement ratio concrete? Let's look at these two cases. So here we have 0.5 water cement ratio, and the bottom is 0.3 water cement ratio. Okay. So after the initial set, the concrete is hardened. Okay. when the water sediment ratio is high enough, okay, and we know because of chemical shrinkage, it will generate pores inside both concrete. However, for concrete with high water sediment ratio, the pores will be fully saturated. So that means we have actual water remains in the smaller pores, even when we have 100% of degree of hydration. So R equal to 1. So 100% of degree of hydration. Because the pores is not dries out, then there's no shrinkage stress. Okay, so the reason for shrinkage is due to drying of the pores. So remember that for now. Okay. For concrete with lower water to cement ratio, okay, the pores will dries out. So the internal RH in the pores and the pore fluid pressure will reduce as smaller pores are empty. Okay, so the pores could be dried out due to either self-desiccation in the case of autogeneous shrinkage, or due to evaporation in the case of dry shrinkage. So whenever the pores dries out, especially drying of the smaller pores, will have a lot of shrinkage stress. And that shrinkage stress will cause the concrete to shrink. All right, so mechanism of shrinkage. So both autogeneous shrinkage and dry shrinkage is dominated by capillary surface tension mechanism. So when the water leaves the pore system, the curved menisci will develop. Okay, so that will create a reduction in relative humidity and a so-called vacuum, which is under pressure within the pore fluid. Okay. The shrinkage stress is affected by many factors, as we can see from here. Okay. The under pressure in the pore fluid, which is PV is double prime minus P prime, okay, is affected by many factors. And the next slide showing P double prime is the vapor pressure, P prime is the pore fluid pressure. The difference between these two is the shrinkage stress. Okay, and they are affected by surface tension of the pore fluid, the temperature, the size of the pore or the pore radius. Okay, because these three factors are affecting radius of the menisci, the curvature. The higher the curvature, the stronger the shrinkage stress. Okay, and here shows because shrinkage reducing admixtures. This is one type of chemical admixtures. It will reduce the surface tension. That's the reason why it can reduce the shrinkage in concrete. Okay. Okay. And radius of pores will affect by the hydration, drying inside and outside. Okay. And here is another set of different parameters. Okay. For example, R is the radius of the pores, okay, and the gamma is the surface tension. RH is the internal relative humidity inside the pores. R is the universal gas constant, doesn't change too much. T is the temperature, also doesn't really change as much. And V prime is the molar volume of water is also constant. Okay, so the main change is relative humidity, the surface tension of the pore fluid, gamma, and also the size of the pores, okay, which is R. Okay, so as you can see from this equation, we call that Kelvin-Laplace equation. When we reduce the pore size, gamma we increase the shrinkage stress, which is the difference between vapor pressure and the pore fluid pressure. If we reduce the surface tension gamma, okay, that will reduce the shrinkage stress. Okay. If we reduce RH, RH is the relative humidity. For example, 80%, this is the natural log of 80%, which is 0.8. Okay, but we have negative here. So that means when we reduce RH, will increase the shrinkage stress. Okay, so use Kelvin-Laplace equation, we can somehow quantify how much shrinkage stress the concrete will experience. Okay, and this is useful to both drain shrinkage and autogenous shrinkage. All right, so come back to this curve. This is for drain shrinkage. And we know, for example, the region 2, which is drying from smaller pores, we can see the slope. The slope of the curve is much steeper compared with region 1, which is water loss from the larger pores. Okay. The reason for that is because when water loss from the smaller pores, so the pore diameter is reduced. So as a result, the shrinkage stress will be increased. So for the same amount of reduction in RH, we see more shrinkage in region 2 compared to region 1. Okay, so we can use Kelvin-Laplace equation to explain the curves. Questions or comments for this?
No.
Yes. Oh, okay. All right. So let's continue. So in summary, what will affect shrinkage of concrete? Many factors. For water cement ratio, if we increase the water cement ratio, drain shrinkage will increase because we have more water. Okay. And also the permeability of concrete is higher, so water will be easy to evaporate. So we're going to have a higher drain shrinkage. Okay. But autogenous shrinkage will be lower because we have less self-desiccation. If we increase the amount of aggregate, the shrinkage will be lower because aggregate will not shrink, only cement paste will shrink. The stiffness of aggregate will also be a factor. The stiffer the aggregate, the restraining effect of aggregate will be higher, so shrinkage will be lower. The bond strength is also kind of important, which is the strength, the bonding strength between the aggregate and the cement paste. So the higher the bond strength, shrinkage will be lower, okay? Because again, the restraining effect of aggregate will be higher. Okay. For environmental conditions, okay, RH, temperature, and wind will affect drain shrinkage and plastic shrinkage. Okay. Age of curing before drying. So increase age of curing before concrete dry, that will reduce the shrinkage because concrete at later age will be stronger to resist the shrinkage stress. If we increase the volume to surface ratio, shrinkage, drain shrinkage rate will be lower, but the total shrinkage will be the same for drain shrinkage. Okay. All right, so that's shrinkage. Okay. Next, let's look at creep and relaxation. Creep means when we keep the same amount of stress stress level constant, the strain will increase over time. Okay. Creep is also caused by slippage of the CEE688 sheets, which is the same as the reason for joint shrinkage. Okay. Relaxation is reduction in the internal stress if we keep the strain constant. Okay. So this is the old slides we discussed before. Okay. And creep in concrete will occur at room temperature, actually at any temperature, as long as the concrete is under load. Okay. Creep can result in a lot of long-term deformation, up to 3 times of the instantaneous deformation. Okay. Can also cause loss of pre-stress in the rebar, because the concrete will become smaller. So the tensile stress in the pre-stress rebar will be lower. Okay. And cracking can lead to deterioration, increase the chemical attacks. Okay. Too much deflection can cause serviceability problems. Okay. But sometimes creep relaxation can be beneficial, can reduce the internal stress in some cases. All right, so this is the, for example, the surface load deflection over the long term can be very large, can also cause loss of pre-stress, the tensile stress in the pre-stressed rebar. Okay. Can also cause stress redistribution because this is the reinforced concrete beam. For example, the concrete will creep, so the rebar, which is the black area, will take more load. Okay, so the stress will be relieved in the concrete. Okay. Okay, so here we talk about concrete deflection under loading. Okay, so at T1, we apply the load, and TU, we remove the load. Okay, and we know concrete is so-called viscoelastic materials. So concrete has both the elastic component and the viscous component. Okay, as we can see here, at T0, if we apply the load, so part of the response is elastic, and the other part is increased over time. Okay, and if we remove the load, okay, so the elastic response will be recovered instantaneously, but for the creep part of the creep can be recovered. Part of the creep is permanent. Okay, the permanent part of creep is caused by the slippage of the CEE688 sheets. Okay. And here shows the so-called basic and the drying creep. Okay. So here shows 3 curves. The first curve, which is the green one, shows us the deformation due to basic creep, which means when the concrete does not have any drying, okay, just under the load, that part of creep is called basic creep. Okay. When the concrete is under shrinkage, okay, remember shrinkage will cause shrinkage stress. So we have some internal stress, and that part of stress will cause concrete to creep. Okay, and that part we call that drain creep. So drain creep is different from shrinkage deformation, okay, which is this part. And the final curve is the green curve, is the deformation due to drain and creep. So that will including drain shrinkage deformation, the creep due to load, and creep due to shrinkage. Okay, so I know it's kind of confusing, but you know, so that's what happened when concrete is under both loading and drying. Okay. This is similar. Concrete has shrinkage. When concrete has shrinkage, it could come in from temperature change, or coming from drying shrinkage, or coming from the autogeneous shrinkage. Okay, different mechanism. Right. So creep is caused by slippage between adjacent CSH sheets under the shear stress. So the CSH sheets is the list of black layers, black lines. Okay. And slip increase when absorbed water between the CSH particle increase. Okay, which is this water. Okay. The less amount of water, the less creep. So this is similar to dry shrinkage. So less water, less creep, less water, less dry shrinkage. And you will see for different parameters, they will affect creep and dry shrinkage pretty much the same, because the mechanism of shrinkage and creep is pretty similar. It is caused by slippage of the CSH sheets. Okay, so external factors affecting creep. So degree of hydration will reduce creep. So that means if we increase the degree of hydration, creep will be reduced. If we increase RH, the creep will be reduced. Increased wind speed, creep will be higher, and so on. Okay, and you will notice this factor will affect creep and dry shrinkage exactly the same. Internal factors. Okay, so here means if we increase W over C, creep will be higher. So same thing for dry shrinkage. Increase moisture and water content, creep will be higher. Again, same thing for dry shrinkage. Okay, and you can see for the remaining internal factors affecting shrinkage and creep the same way. Influence of loading on creep. Okay, so creep is caused by stress inside concrete. And that stress could come in from loading, could come in from shrinkage. Okay, so as a result, if we increase the amount of load, okay, creep will be higher. Right, so it makes sense. If we increase the age at loading, okay, for example, at the green line is we apply the load at about 13, 14 days. So the creep will be lower compared to where we apply the load at early age. Because at early age, concrete is weaker. If we apply the load earlier, creep will be higher. All right, so prediction of creep, people have different ways, different researchers have different equations trying to predict the amount of creep, but this is a very rough estimation. Okay, just show you some example. Okay, we can use some kind of equation to predict the creep at a certain time based on the ultimate creep, which is the CULT, which is for ultimate or the final creep, and also a function of time. Okay. Okay. And we can also use viscoelastic model to simulate the behavior of concrete. Okay. The viscous component can be seen as a dash point. And elastic component can be seen as a spring. Okay. And if we think the viscous and elastic component in series, okay, then the stress for the elastic component will be same as the stress in the viscous component. Okay, but the strain will be added together. If we think the viscous component and plastic component as in parallel, then the strain in the elastic component will be the same as the strain in the viscous component. Okay, and the stress level will be added together. Okay, and then we can think like the combination of in series and parallel. Okay, let's show here. So here shows how a concrete will crack. Okay. So initially we have brand new pristine concrete, has no crack whatsoever. And the crack will develop due to many reasons: shrinkage, creep, loading. Okay. And when cracks occurs, it will widens up due to further loading or physical or chemical effects, such as freeze-thaw damage, corrosion of reinforcement, which we'll discuss in future lectures, soft attack, DSR, and so on. Okay. So eventually, it will result in further cracking, even spalling of the concrete from the rebar. So rebar will be exposed until total corrosion and the reinforced concrete member will fail eventually. Okay. If the shrinkage is not restrained, then it really does not matter. Okay. But if the shrinkage of concrete is restrained, then the stress will be developed inside the concrete. And then concrete may crack if the stress level is high enough. Okay. So cracking occurs as a result of low toughness, low strength of concrete combined with higher tensile stress. If the tensile stress is higher than the toughness, then concrete will crack. Okay, so when shrinkage will cause concrete to crack, so that is depending on the strength over time and also the strain, the stress over time. Okay, so the blue line shows the stress level due to shrinkage, for example. Okay, and green line shows material resistance or the strength of concrete, which is also going up over time because of hydration. Okay, so concrete will crack when the stress level catch up the strength of concrete. Okay, then concrete will crack. Okay, however, things will be more complicated than this, unfortunately, because we have creep and also relaxation involved. Okay. So let's look at this virtual experiment. So initially we have a specimen here. If the shrinkage is not restrained, then we have free shrinkage. So we have no tensile stress in the concrete. Okay. If the shrinkage is restrained, then we have sigma shrinkage, which is the shrinkage stress, the stress due to shrinkage. Okay, but the stress will cause the concrete to creep. Okay, which means if it is tensile stress, the concrete will become longer. Okay, then we have smaller stress level because the stress will somehow relax. So stress relaxation is equal to stress due to shrinkage minus the stress due to creep. Okay, so that is equal to the final stress state. So the final stress state will be affected by shrinkage stress plus creep effect. Okay, and the creep effect will cause the stress level to be relaxed a little bit, okay, which is a good thing, okay, because that will reduce the final stress level. And we could use the ring test, which is set up in this picture, to stimulate the shrinkage, restrain shrinkage in the strip. The experiment is very easy to do, and we can simulate the restraint effect by only on the end, okay, like in this case, or we can simulate the restraint not only on the two ends, but also in the bottom, such as the case of a pavement, for example. Here, just show an example of using the ring test to study the effect of I think some type of fibers, okay, different dosage of fibers on the size of the crack. Okay, if we increase a certain type of fiber from 0 to 1 to 2%, then the size of the crack will be smaller. Okay, so we can use this to quantify the shrinkage and also crack in different type of concrete. Okay. Right, here shows another example. So high strength concrete increase potential for shrinkage cracking. Okay, so again, they use the ring test. We can observe the size of the crack. Okay, and here shows the different specimen at which day it will generate the first cracking. Okay, so the concrete will experience a different percentage of RH, which is relative humidity. So at lower relative humidity, the concrete will crack early. Okay, so for the same type of stress level. Here shows another study, how the fibers will affect shrinkage cracking. Again, we'll have a dedicated lecture about fiber reinforced concrete and other high performance concrete. Okay. So here shows plain concrete, which is blue line. The pink line is 1% of polypropylene fiber. The black line is 1% of steel fiber. Okay. So what we can see is the concrete with fibers will reduce the free shrinkage somehow. Okay. And here shows how the fiber reinforcement percentage will affect the size of the crack. Okay. So increase the percentage of the fibers, the size of the crack will be lower or even reduced to 0. Okay. And they use different type of fibers. Okay. And here is another example, how SRA, this is shrinkage reducing admixtures. So increase dosage of that, we can reduce the shrinkage strength. Okay. So we can use Kelvin-Laplace equation, which we just discussed 15 minutes ago. Using shrinkage reducing admixtures, we can reduce the surface tension in a pore solution. As a result, we can see the shrinkage strain concrete is lower. And what is this? This is showing us the shrinkage may not be uniform in different part of concrete. Okay, because the drying may not be uniform in concrete, especially for drying shrinkage. Okay, so this is the concrete slab. The concrete close to the ground has higher RH compared to a concrete closer to the air. So as a result, we have a moisture gradient. The concrete near the air will be drier compared to concrete near the ground. So this moisture gradient will cause a shrinkage strain gradient, which means the concrete close to the air has more shrinkage compared to the concrete closer to the ground. So that may cause the slab to curve. Okay, we have curling in the slab. And here shows another example. So this is a variable restraint example. This simulates the behavior of a bridge stack. Okay. I think in this study, this is the actual strain. ACT is for action. They consider creep effect, okay, and also the restraint effect because the concrete is restrained by the bottom and also the two end. Okay, and also they use a different dosage of shrinkage reducing admixtures. Okay, because shrinkage reducing admixture can reduce the shrinkage level, so the stress level will be lower if we use SRA. Okay, so that will prolong the time the concrete will crack. So this model can predict when concrete will have cracking depending on the dosage of shrinkage reducing admixtures and also the depth restraint. Okay, so let's consider all these factors we described before. All right, again, just show you an example of people study shrinkage and creep. Okay. So today we discussed a very complicated mechanism, shrinkage and creep. Okay. For shrinkage, we have 5 different types of shrinkage, okay, including dry shrinkage, plastic shrinkage, autogen shrinkage, carbonation, and chemical shrinkage. Okay. Shrinkage is more important compared with creep. Okay. Creep is caused by very similar mechanism as dry shrinkage, which is the slippage of the CSH sheets. Okay. And we discussed different external and internal factors affecting shrinkage and creep. Sorry, dry shrinkage and creep, which pretty much the same way. And what is the influence of aggregate on the volume stability of concrete? More aggregate, concrete will have less shrinkage and less creep, because remember, only cement paste will shrink and creep. Okay, aggregate will not do that. At least aggregate will not shrink and creep as much as the cement paste. All right, that's the end for lecture number 11. Okay.